Okay, so today we'll be going over oxidation numbers. So oxidation numbers are basically the summation of all of the different charges that go into a compound. So if you're looking at something like water, H2O, or some other compound, it either has a neutral charge, which means that it doesn't have any charge attached to it, or it could be something that has a charge on it, in which case we have to account for it. Oxidation numbers are calculated using the periodic table. Some elements have set oxidation numbers, while others can be adjusted to fit certain chemicals. So one of the most common ones is oxygen. I just have the periodic table opened up here as well on this side of my screen here, which is -2. And that's because it is two rows, or not periods, but groups away from the main noble gases over here. And that's just like one of the most standard ones. And then there's only a few case points where it's not equal to -2, and that would be when it's in a diatomic molecule. So in H2O2, O3, O2, and I'll send you this whole list of rules and things that go into it. But for the most part, that will be a good reference, because if you're going to be tested on things of this nature with oxidation numbers, oxygen will usually be incorporated in some way. So just looking at a simple one, I was going to use water as the example. So if you look at water, it is composed of H2O, and you'll notice that it does not have a charge attached to it, which means that it is a neutral compound, or again that the charge is equal to 0. You start by writing out H2O, yeah, and I put in however many moles of hydrogen and however many oxygen. So in this case there are 2 hydrogens and 1 oxygen. And then the oxygen, we know, has a charge of -2. It's a good way to start it, and then we'll know how to go from there. So -2 plus, then you have the 2 hydrogens, and that is set equal to 0, because again the neutral charge is what we're adding to try, that's what we're trying to find with these oxidation numbers. So if you look at here, you can see my work thus far. It's just that hydrogen, we're looking for hydrogen. We know oxygen is -2, and the net charge is equal to 0. So now that we have that, we just set the charge for hydrogen equal to x, and then you can kind of fill in from there. So you would have 2x minus 2 is equal to 0, add 2 on the other side of the equation, 2x is equal to +2 divided by 2 both sides of the equation, and x is equal to 1. Hydrogen, again, is one of those that's pretty standard, but it can change under certain conditions. But it's if you get like a crib sheet or something like that, the rules for oxidation is something that you should put on there. If they do put irregular ones on there, usually they're pretty straightforward. Hydrogen being +1, oxygen being -2, and so on. Some of the other rules that go into this that are pretty straightforward, the alkali metals and also the alkaline earth metals are standard set at +1 and +2. So that being the ones all the way to the far left of the periodic table, having a +1 charge, and the alkaline earth metals having that +2 value. Another one, of course, is oxygen, which is -2, but most of the other ones are flexible in some way or form. They can be changed to suit a certain charge, so you can't really rely on just counting over 1, 2, 3 for a +3 charge. Just as an example, something in the middle of the periodic table, so looking at like the transition metals, you like iron or cobalt can be changed to better suit different compounds. That's why you have iron 2 and iron 3 compounds, because their charge can change because of that. So yeah. But yeah, as an example of that, I'll give you one that's kind of a little bit more weird. Polyatomic ions are a good place to look for examples of this kind of oxidation adding, and where it can change elements' charge based on just trying to get it to that correct charge. But using things that we do know for certain to find the correct value of that maybe uncertain charge. So what I'm looking at right now is SO42 negative, which we know to be, I think it's sulfate, if I'm not mistaken. But regardless of what it is, the chemical compound is SO subscript 4 to the 2 negative. So looking at this one, we know that oxygen has its -2 value, and it's not in a special case where it's going to have a different charge to it. So we can see that oxygen has 4 iterations of itself, or 4 moles. So you put 4 times the -2 value, which we know, add that to X, which we will sub in for the charge of the S value, and we set that equal to -2, because that's the ultimate charge of the compound that we're looking at. What? So yeah, so what we're looking at here is X plus 4 times -2 is equal to -2. So if you simplify that, we get X minus 8 is equal to -2. And you add 8 on both sides of the equation, and you get positive 6 here for X. So in this, we know that S's charge, in this case sulfur, I believe that's what S is, yeah, sulfur, has a charge of positive 6. And when looking at the table, or just the periodic table, if you count over normally, you would think that would have possibly a -1 or a -2 charge, but in this case it actually has a positive 6, so something completely different than what you would think. This is because you go over from the opposite side of the periodic table in this instance. You start it at the left side, which is sodium to magnesium, aluminum, silicon, phosphorus, and sulfur, so 1, 2, 3, 4, 5, 6, and sulfur actually has a positive charge 6 instead of that -2 that you would expect. And this is just a classic case of the flip-flopping that can go on when they're trying to accomplish that overall charge that it gives you. But yeah, I'll send you the links to this rule sheet, and also the periodic table with the oxidation number, as well as a photo of my work here, and I hope this helps. Thanks.